Hello everyone. Today we are going to analyze one-dimensional energy eigenvalue problems. Specifically, to begin with, we will be dealing with free particle problem in one-dimensional energy eigenvalue problems. So, what is an energy eigenvalue problem? We have already learned Schrödinger equation, and we know that Schrödinger equation is the basic equation analogous to Newton's equations in classical mechanics. Since Schrödinger equation is the basic equation in quantum mechanics, in order to analyze quantum mechanical systems, or in order to study quantum mechanical systems, we should begin with Schrödinger equation. I mean to say that to begin with Schrödinger equation, our basic task in solving a quantum mechanical problem is to find out the proper equation of or Schrödinger equation, proper Schrödinger equation for that particular system or that particular example we are dealing with. So once we have finalized the form of Schrödinger equation, so when I say the form of Schrödinger equation, you have to understand that the term that varies with different systems or different examples is the Hamiltonian. As you know, Hamiltonian is the sum of kinetic energy and potential energy for a given system. So our task is to find the Hamiltonian or kinetic energy and potential energy of the system, so that the sum of kinetic and potential energy gives Hamiltonian for that particular system or for that particular example. So once we have finalized with the Hamiltonian of the given system, we apply it in the Schrödinger equation and find the possible energy eigenvalue solutions and the eigenfunctions for that particular system. That is what we are doing in a basic quantum mechanical problem. So this you can just look at this equation 4.1. So equation 4.1 is a time independent Schrödinger equation. As you can see, the left hand side gives the Hamiltonian operator. The meaning of the left hand side is that the Hamiltonian operator operates on a wave function. So Hamiltonian operator consists of two parts. This is the kinetic energy part, that is minus h cut square by 2m d square by dx square, and v of x is the potential energy part. So as I mentioned in the beginning, we need both kinetic and potential energies, and that constitute the Hamiltonian operator. So when the Hamiltonian operator operates on the wave function psi of x, gives the energy eigenvalue capital E of the system. And so that we can find the energy eigenfunctions. So let us check how this is done in various quantum mechanical systems. To begin with, we are going to analyze free particle solution. So when I say free particle, we have to think about the kinetic and potential energy of this free particle. Kinetic energy is significant in the case of a free particle, but what about the potential energy? When a particle is a free particle, it feels zero net force acting on it. So we are going to consider such a free particle having mass m and moving along the x-axis for making the mathematical calculation easier, and no net force acting on it. What do you mean by no net force acting on it? So when there is no net force, you know that potential force is force can be written as minus gradient of potential. So when force is 0, dou V by dou X is 0, and that implies our potential V is a constant. So when the particle experiences a constant potential, we can say that the effect of potential is negligible, or we can say that the particle feels the effect of potential everywhere equally, so that we can consider the V as 0. When we say both the potential is a constant as well as potential is equal to 0, it gives the same effect. So in this case, in the case of a free particle, we can say that the potential is constant. So what are we going to do? We are going to give the value of potential as 0, because it is meaningless in giving the value of potential and analyzing the equation. So our time independent Schrodinger equation reduces to only the Hamiltonian. The Hamiltonian reduces to only with its kinetic energy part. So the equation is reduced to this form that is shown in 4.122, that is minus h cut square by 2m d square psi of x by dx square is equal to E psi. If we rearrange it, taking minus h cut square by 2m to the right hand side, you can rewrite it as d square psi by dx square is equal to minus k square psi. I think you can do it easily. So, okay, I think I will show you how it is done. Okay, so our equation now is minus h cut square by 2m d square psi of x by dx square is equal to E into psi of x. So d square psi by dx square is equal to minus 2m E by h cut square into psi of x. This means that Yeah, this means that 2me by h cot square is taken or assigned with a value k square. So our equation reduces to, this is equal to d square psi by dx square is equal to minus k square psi, or we can take this one to be right hand side, plus k square psi is equal to 0. This is what written on 4.122. Now, what about the solution of the system? So when we think about the differential equation, as you know, this is a differential equation. What we have written down is a differential equation. So the possible solutions, if we analyze this kind of type of differential equation, and the possible general solutions look like 4.123, that is I of x is equal to a e raised to I kx and also a e raised to minus I kx. So we can say that this free particle solutions are degenerate. Different eigenfunctions corresponding to the same eigenvalue. But we know that the energy has to be real and positive to make the eigenfunction finite at x is equal to plus or minus infinity. Also, if we analyze these two solutions, e raised to I kx corresponds to particle moving in the positive x direction with the momentum h cut k plus h cut k, and e raised to minus I kx corresponds to particle moving in the negative x direction with the minus h cut k momentum. But the energy is the same in both the cases, and the eigenvalues, all real positive eigenvalues, are the allowed eigenvalues. So since we have this particle solution, degenerate solution, we cannot just go on with the solution, these two possible solutions, since it represents a continuous plain simple harmonic wave. So what do we do? The thing we can do is to think about possible normalization. Because using this 4.123, we cannot normalize a wave function. So whenever we analyze a quantum mechanical system, one of the conditions we choose in order to completely solve the solution is that the wave function should be normalizable. If it is normalizable, it is easy for us to calculate the values, energy eigenvalues and energy eigenfunctions. So let us now think about the possible normalization so that we can solve the free particle Schrodinger equation.